Hi everyone, we're working group 4 and I'm Abhiram Raju.
I'm Sophia Myers.
I'm Hubery. Hi.
I'm Noah Peralez.
And I'm Anna Shifman.
Over the past few weeks, we have worked on a research project, remote sensing correlations between income and land cover to analyze urban heat islands in Austin, Texas. Our goal with this research was to investigate what factors affect the formation of urban heat islands and how they correlate with each other. Through this, we hope to shed light on income land cover patterns to potentially assist future urban planning.
Every year, NASA sees interns choose an area of interest AOI of 37 points to classify based on land cover. We utilize the 14 AOIs in Austin, Texas from 2022 to 2024 and use the land cover data to investigate how factors such as impervious surfaces, which is concrete and asphalt, greenness, and median household income affect the formation of urban heat islands, UHIs, the phenomenon in which certain areas of a city experience extreme heat at a higher rate than others. We expected to find that as land surface temperature and percentage of impervious surface increase, greenness and median household income would decrease.
We derived our datasets from 3 different sources for this project. We obtained our percentages of greenness and impervious surfaces for each AOI from the Globe Observer database via Collect Earth Online, and we used the same to collect on-the-ground photos from each AOI to validate our land cover data. We use NASA Appears to request land surface temperature data, or LST data, for our AOIs from the EcoStress instrument on the International Space Station. Finally, we use the United States Census Bureau to find datasets showing the mean and median household incomes for the city of Austin.
Cross-checking land data with global observers help create variations in remote sensing data. This identification allows for local variations and for researchers to cover large areas and obtain more frequent updates.
We use k-means clustering and unsupervised machine learning model to classify UHIs in our study. To find the optimal number of clusters, we evaluated the silhouette score, Davis-Bouldin index, and Kalinske-Haribas index, which indicated that 2 clusters were the best fit. On the right, you can see the clustering result where each coordinate is grouped into high or low UHI risk. Our analysis showed that socioeconomically disadvantaged areas have higher risk of being UHIs. This is evident in the left graph, which compares the mean income values by risk level, showing that high-risk areas have lower median and average incomes. The right graph highlights the environmental factors, demonstrating that high-risk areas have less vegetation, more impervious surfaces, contributing to higher UHI risk.
We also carried out hierarchical clustering. The left plot here displays the results of the clustering analysis on our AOIs. Here, after calculating the same indexes for hierarchical clusters, the optimal number was 3 clusters. So 0, 1, and 2 represent high, low, and medium risk respectively. On the right, we've also generated pie plots for every variable to show the distributions and interactions between them. And over here, the top 2 graphs depict the continuous distribution for the entire data set, while the bottom 2 graphs display the bar charts for income and land cover cluster-wise. The high-risk cluster has low incomes and vegetation, but high impervious surface percentages. But the low-risk cluster, on the other hand, has high incomes and vegetation, but low impervious surface percentages. This shows how our clustering helped unravel trends in the data to identify areas at risk of becoming UHIs.
We also use dbScan because it handles noise and outliers well, which is especially useful when working with real-world data. As displayed, the clusters formed or differentiated within specific AOI points, unlike what we saw in k-means. In these clusters, we found that as income increased, so did vegetation, and in areas with lower income, there were, on average, more impervious surfaces. This is especially apparent in clusters 0 and 1, which follow the trend described previously. We hypothesized that UHI risk would increase with a higher percentage of impervious surfaces and decrease with increased greenness and median income. Regression analysis confirmed our hypothesis about the relationships. We found that there was a weak negative correlation with a p-value of 0.02 between impervious surfaces and income, and weak positive correlation with a p-value of 6 times 10 to the power of negative 18 between greenness and income. However, we want to note that once land surface temperatures were included, the data set was very incomplete. The clustering algorithms were not as effective in describing trends, and LST actually had very minimal correlations with the other variables, as it was relatively consistent throughout Austin. And thus, we want to strengthen our research in the future by expanding to California for a more diverse data set.
There are several potential sources of error in our project that may have affected our final correlations. The EcoStress instrument takes LST measurements at different times of day, so the timing for each data point was not consistent. 2 AOIs lacked impervious and greenness data, and some AOI points did not have corresponding ground photos on Globe Observer, preventing us from cross-checking them. Overall, our team members said that the NASA Seas internship allowed us to enhance our skills, learn what a STEM career might look like in practice, and make meaningful connections with like-minded individuals. The unique challenges presented helps us grow as people and scientists, too.
We'd like to thank everyone who helped for the contributions. Please scan the QR codes to explore all the data sets and to view our detailed poster.